Okay, so first thing that we need to remember is with velocity, if I'm asking you for a velocity function, velocity is going to be the first derivative of a position time function. Okay, so essentially what velocity is, if we were doing limits, you would have a position time graph, and I would take a point on the position time graph, and I would say that velocity is equal to the limit as time approaches 0. And it's the change of s, delta s, over delta t. Okay, it's just giving you the instantaneous velocity at a particular point in time, but it's the first derivative of the position time function. So for this graph here, if I said to you, from the interval of a to b, what's happening, you would say, okay, from a to b, if this is a position time function, then the slope at any point will give you the velocity. So if we drew a tangent line at that point there, v of t would be greater than 0. This slope is a positive slope. So what that means is it means that v of t is greater than 0. What's happening at point B? So at point B, if we were to draw a tangent line, remember that the slope of the tangent gives you the velocity. So at point B, v of t is equal to 0. That's when the object's at rest and it's going to change position. From B to C, what's happening, again, the slope at any point along that interval would give you the velocity, right? Because slope is going, the derivative of this would give you the velocity, and the velocity is less than 0. So v of t is less than 0. At c, it's changing direction. Velocity is equal to 0. And then on the interval from c to d, what's happening here is the velocity is greater than 0, because all of the slopes from the interval c to d would be greater than 0. Okay. For acceleration, um, if I said, okay, so what would a of t equal? A of t, the acceleration function, it's the first derivative of the velocity function, or it is the second derivative of the position time function. Would be the acceleration function. What's important with acceleration, and this is what sometimes students have a hard time understanding, is this right here. So looking at velocity and acceleration and figuring out, is an object speeding up or slowing down? So what happens is if velocity and acceleration have the same sign, so they're either positive and positive, or they're both negatives, the object will be speeding up, because a negative number times a negative number will give you a times v is greater than 0. So if you get a times v is greater than 0, we're going to be speeding up. If those two signs are opposite signs, a times v will be less than 0, the object is slowing down. So I'll show you what this means by looking at this chart here. Okay, what we're given is we're given the acceleration of an object is 4 meters per second squared. Or, remember that acceleration, it's the derivative of velocity. So here's 4 meters per second per second. So what this means, so let's just quickly write what this means. What this means is the velocity. So if you're given an acceleration of 4 meters per second squared, what does that mean? It means the velocity is increasing 4, so it's going up 4 meters per second every second. So an acceleration of 4 meters per second squared means that the velocity is increasing 4 meters per second every second. So what we're going to look at is we're going to look at the velocity when velocity is greater than 0 and when velocity is less than 0. And we're going to pick just like a starting velocity. So let's say I want to start at a velocity of 10 and a velocity, if I'm going to pick negative, a velocity less than 0, I'm going to say negative 10. Okay, so at 1 second, what would my velocity be if I'm increasing by 4 meters per second every second? What would my velocity at 1 second be? 14. So if I'm increasing by 4 meters per second every second, at 1 second, my velocity would be 14. And at 2 seconds, my velocity would be 18. Now, some students will look at this and they're all positive numbers and they'll say that the object is speeding up, and it is speeding up. But how I like to see that it's speeding up is it's going to be speeding up if a times v is greater than 0. So the acceleration that I was given was a positive number. So acceleration was positive. The velocities, 10, 14, and 18, these are also positives. A positive times a positive will give you a number greater than 0. Therefore, the object is speeding up. Okay. If we look here, if we're at a velocity of negative 10 and I'm going to increase by 4 meters every second, this would give me a velocity of negative 6 and then a velocity of negative 2. This object is slowing down. Okay, so why is it slowing down? We got to see what the sign of a times v is. Acceleration was 4 meters per second, which is a positive value. These velocities are negative. A positive number times a negative number will give you something less than 0. And whenever we get less than 0, we're slowing down. Okay? Let's do this example. If our acceleration is negative 3 meters per second squared. So again, what does that mean? What an acceleration of negative 3 meters per second squared means, it means the velocity is decreasing. So it's going down by 3 meters per second every second. Okay, so let's look again at when the velocity is greater than 0 and when the velocity is less than 0. And let's start with a velocity of 10 and a velocity of negative 10. If I'm going down by 3 meters per second every second, I'm going to go from a velocity of 10 to 7 to 4. Now, this object would be slowing down. But how I know it's slowing down is a times v. Acceleration was negative here, and velocity is positive. These are all positive velocities. A positive number times a negative number is less than 0, and that indicates your object is slowing down. These ones here, if I go down, if I'm at negative 10 and I'm going to go down, velocity is decreasing by 3 meters per second every second, this would be negative 13 and negative 16. From here, I would have a times v, acceleration is negative, velocity is negative. This object is actually speeding up. So a times v, 2 negatives will give you something greater than 0. Therefore, we're speeding up. Okay, I'll show you how this would relate to a question. On the quiz that I gave you, look at the very last question on the quiz, which would be this guy. The position of a particle is given by this position time function formula here. When is the particle slowing down? So a particle is slowing down when a times v, is it going to be greater than 0 or less than 0? Less than 0. Okay, so I want to look at my velocity function and I want to look at my acceleration function. I'm given my position function. So my velocity function, v of t, it's going to be the first derivative of the position function. So the first derivative of the position function would give me 3 over 3, so that would give me t squared minus 12t. I want to know, we need to figure out the signs, right? So I want to know a and v. So what we're going to do is we're going to take our velocity function, so v of t is equal to t squared minus 12t, set that equal to 0, and let's factor. We would get, factor out a t, and we're going to get t minus 12. So we're going to have 2 times that we're going to look at, 0 seconds and 12 seconds. And we're going to look at the intervals between 0 and 12 and greater than 12, and we're going to figure out when is the velocity greater than 0, when's the velocity less than 0. Okay? So if I put this on a number line, 0 and 12, and this is my velocity. So if I pick a number between 0 and 12, so let's say I pick 6 seconds, and I put 6 seconds into this function here, I'm going to get a positive number, and here I get a negative. So from 0 to 12, my velocity is negative. Greater than 12, my velocity is going to be, if I pick 15, positive times a positive is going to be positive. Okay, so there's my velocity. Let's look at the acceleration function now. So the acceleration function, a of t, it's the derivative of the velocity function, or it's the second derivative of the position time function. So a of t is equal to, Shaywa, what would a of t be equal to? 2t minus 12. Set that equal to 0 and factor. Let's factor out a 2, and we're going to get t minus 6. Time here is 6 seconds. Okay, we're going to check when is our acceleration positive, when's our acceleration negative. Now, what I want you to do is I actually want you to kind of line up your number lines. And let's put acceleration here. And we've got 6 seconds. So I'm just going to put 6 here. Okay. So less than 6 seconds. So let's say we picked 3 seconds. What would my acceleration be? At 3 seconds, is my acceleration positive or negative? Negative, right? So if I put it into my acceleration function here at 3, I'd have a negative number. So let's put a negative number here. Greater than 6 seconds, so let's say I picked 8 seconds, I'm going to have a positive acceleration. It's hard to see where these line up, but here's how we're going to do this. On this number line, I want you to put a 6 on this number line as well. So just put a 6 here. And on this number line, I want you to put a 12. Okay. From 0 to 6, it would be negative and negative. So is the object speeding up or slowing down if from 0 to 6 it's 2 negative numbers? It is speeding up. A negative number times a negative number, it would be speeding up. From 6 to 12, over on this graph, 6 to 12, this is negative, and this guy is positive. I've got negative times a positive. So from 6 to 12, a times v is less than 0. It would be slowing down here. Beyond 12, on my velocity, I've got a positive. And what would I have for my acceleration beyond 12? Would I have a positive or negative number? Positive. Like beyond 12, if I picked 15, it'd be a positive number. So After 12 seconds, I've got positive times positive. A times V is greater than 0. It would be speeding up. So the question was, when is the particle slowing down? The particle is slowing down between 6 and 12 seconds. So the particle is slowing down from 6 seconds to 12 seconds would be when the particle is slowing down. Okay, let's look at acceleration now. Okay, what you're gonna have to be careful of for your exam is you won't know if, well, you'll know, you got to be careful whether it's a velocity time graph you're getting or if it's a position time graph. Okay, so if it's a velocity time graph, the slope on a velocity time graph, what would it give you? It would give you acceleration. So the slope on a velocity time graph would give you acceleration. Okay, so if you take the derivative of your velocity time graph, you're going to get your acceleration. So if I said what's happening from the interval A to B, so A to B, the slope of this is positive, but the slope is acceleration. So acceleration according to time is greater than 0. So acceleration is a positive number here. At B, because this is a velocity time graph, the slope at B is 0, but what is the slope? The slope is the acceleration. So A of t is equal to 0. So at point B, acceleration is equal to 0. From B to C, slopes are negative, but slopes are acceleration because we're on a velocity time graph. So from B to C, my acceleration is going to be less than 0. At point C, my acceleration is going to be equal to 0. And from C to D, the slopes are positive, which means the acceleration is greater than 0. A of t is greater than 0. Okay. Students tend to be good if I give them a velocity time graph because they understand a position time graph, the slopes are going to be velocity, and students understand that velocity time graphs, the slopes are going to be acceleration. What's more complicated is this graph. If I give you a position time graph and I ask about velocities and accelerations. So let's do velocity first because this will be the easier of the two. So let's do velocity and then we'll do acceleration. And let's do on the intervals A to B, B to C, C to D, D to E, E to F, F to G. So let's do A to B, B to C, C to D, D to E, E to F, and F to G. Okay, this is a position time function. So the derivative of a position time function, Owen gives what? So like the derivative, the slope at this point is giving you velocity. So now look at all of these like velocities and put either pluses or minuses here. So for example, like Karis, what would the velocity of this guy be from A to B? Positive. Yes. And Carly, from B to C, what would the velocity be? Positive. C to D, Emily, would be what? Negative velocity. Yep. So negative. D to E, Akil, would be what? Negative velocity. E to F, Julie, would be positive velocity. And even though this is going to be considered like a constant line, what would the slope of this line be? Positive. Yeah, F to G, it's positive. Okay, so position time functions, it's easy to see velocity. What's harder to see is acceleration. So what you have to do for acceleration, it has to do with concavity. Okay, so let's write notes up here. If you have a position time graph and you have a section where it is concave up. So here's what concave up will look like. So on a position time graph, this is a position time graph, wherever we have concave up, what's happening is the slopes or the velocities are increasing. Whenever we have concave up, our slopes are increasing. So here's what I mean. How are my velocities increasing? Well, right here, I've got a negative velocity. Here I have a zero velocity. Here I have a positive velocity. So concave up represents that your slopes are increasing. The velocities are increasing. If you have a section that's concave up, you're going to have positive acceleration. Acceleration is going to be greater than zero. So on this graph here, this is a position time graph. Anywhere that's concave up, your acceleration is going to be greater than zero. So this piece is concave up, acceleration is greater than zero. This piece here is concave up, acceleration is greater than zero. Whenever you have your slopes or velocities are increasing, then acceleration is greater than zero. So what that means is from A to B, it's concave up, acceleration is going to be positive here. From D to E, it's concave up, acceleration is greater than zero. E to F, concave up, acceleration is greater than zero. Wherever you have concave down on a position time graph, so from here to here would be concave down. What happens with concave down? This is our shape. If I said what's happening with the slopes of these this, I've got a positive slope going to zero, going to negative. Slopes or velocities are decreasing on a position time graph when it's concave down. Whenever it's concave down, that means that the acceleration is going to be less than zero. So here is concave down. From here to here, acceleration is less than zero. So B to C, it's concave down. C to D, did I mess up? Oh, yes, I see. Okay, B to C, sorry, B to C is negative. C to D is negative. D to E is oh yeah, I see. This guy's positive, you're saying, right? Okay, and then where your acceleration is zero is if you have a straight line. So a straight line, when it's constant, your acceleration will be zero. So here is where my acceleration is zero. So this guy would be zero. Okay, now to figure out, you have to be able to look at this and say, where's your object speeding up or slowing down? So if you multiply v times a and it's greater than zero, it is speeding up. So this times my object's going to be speeding up on the interval a to b. Where else is it speeding up? C to D. Negative times negative will be greater than zero. And one more place. E to F. It's speeding up. Where my object is slowing down is when A times V is less than zero, so when you have opposite signs. And my object would be slowing down, or my particle, from B to C and from D to E. So B to C and D to E. Where my acceleration is constant is from F to G. Where on this position time graph would velocity be equal to zero? C, the slope is zero, and E, the slope is zero. So C and E. Okay.